This is the two-part series on living in space. So it's all about spending long amounts of time in space. What are the issues that we have with that? What are some of the hazards that as potential colonists in something like Mars or Europa is one of the plausible planets for the future, even colonizing the moon if that's something we do when we start doing our asteroid mining processes. There's a lot of things that we need to consider in terms of our own safety, even the equipment safety. So we're going to look at this section. It's all about what are the hazards for humans in particular, about being in space, spending long amounts of time in space, and that kind of stuff. The first thing that comes to mind when we think about space is often radiation. Radiation is a significant hazard if we're in space. On Earth, it's not so bad. We still have a lot of radiation. That's why if you spend a lot of time outside, you get sunburn. It's because of the radiation. On Earth, however, we have something called the Van Allen belt. And this is generated by the Earth's magnetic field, and this actually protects us from a large amount of the solar radiation that comes in. Without that, it would be a very different story. There are a few things that can stop radiation. There is soil, for example, is quite good. So if we were to go to the moon or go to Mars, one way that we could protect ourselves would be to live underground. We would be subterranean species, and we would have these colonies under the planet. It wouldn't be as likely that we've got these cocoons sitting on top, unless they were made of the next couple of materials. And that is something like steel or concrete. Something that's very dense can stop a lot of this incoming radiation, but it also needs to be quite thick. So an example of that is if you've seen any of the documentaries or videos about the Chernobyl disaster. When that first happened, they built this big concrete sarcophagus to encase it, and that worked okay, but there was still a lot of radiation leaking. And after a while, they had to then build the second sarcophagus, which they've only just recently completed. So even concrete is not the perfect substance. Steel, very, very similar. Again, the issue with concrete and steel is the fact that it's extremely heavy. So you imagine if you were going to go colonize Mars, trying to carry hundreds and hundreds of tons of steel on a spacecraft, unless the resources over there, it's not practical to try and cart those across. Soil is probably very similar. You can't exactly line your spaceship with soil. It would just weigh too much, but it's a nifty idea. The other one that you can use is water. Water is reasonably good at either absorbing or deflecting incoming radiation, but again, you need it to either be there waiting for you so that you can harness it and we live underwater or something, or have these giant fish tanks surrounding our houses, or alternatively, you have to take it with you. And that's another issue. Water is also quite heavy. It's a heavy resource to cart up with you. Magnetic fields are effective. If you can generate a strong magnetic field, that will deflect the radiation, just like the Van Allen belts do on Earth. The problem with that is to generate a large magnetic field that's going to extend to a distance of meters in order to encase an entire house or a spaceship or something like that, you need a phenomenal amount of energy. Even just to do very, very small ones in a lab experiment take large amounts of energy. We're talking like kilovolts and things like that. So to then expand that out to this giant electromagnetic field, you would need impractical amounts of energy. So I mentioned before this Van Allen belt. So this diagram here shows sort of a representation of what the belt looks like. So it's a strong field of energetic particles, and these are pretty much radiation that's generated by the Earth's magnetic field. So when I say that, it's not actually made by the magnetic field, it's the magnetic field that generates these belts of it. The radiation is coming in from the sun, and these things are harnessed or deflected or trapped, and they're guided either around or in a circle or something like that. So we end up with these two belts of concentrated radiation because of this magnetic field around Earth. The first one is at around 640 kilometers, and then there's a gap, and then the next one is at about 58,000 kilometers. So that's why we call them the belts, because there's actually two with a gap in between. So anything that travels beyond a low Earth orbit is going to enter the zone of radiation of the first Van Allen belt. Beyond these belts, they face additional hazards from things like cosmic rays and solar particles and stuff like that. You've got the additional radiation of space, but even just traveling through these belts is quite significant. It's far worse than just the general exposure of space because it's been concentrated at these two belts. So even something like a solar cell, an integrated circuit, the circuit boards, your microchips, all this stuff, there's enough radiation in these belts that can fry these. So if you're traveling through, it might just damage all of your computer programs and processors, and then you're pretty much just drifting around in space without a computer. In the early Apollo missions, this was an issue, and they had to design their path quite strategically around these Van Allen belts. But the advantage they had back then was that they didn't have high-tech computer chips. A lot of their computers were relatively simple and didn't use tiny voltages as signals, so they were a lot stronger than modern technology. But obviously you don't have the same data and precision that they had back then. The Hubble telescope, which is pretty well known, it's very famous. It's technically a satellite. It is orbiting around Earth, even though you have this perception of it's just a stationary object filming space. It is actually orbiting. So we would say it's a satellite. Often it passes through very intense radiation sections, not the Van Allen belts themselves, but just kind of these pockets or these surges of radiation. They turn its sensors off when that happens. Otherwise, it'll just fry a lot of its computer programs, could burn out its lenses and things like that. So they're constantly monitoring this. If we had a satellite that was shielded by 3 mil of aluminium in an elliptical orbit, and it passed the radiation belt, it's going to receive about 25 sieverts per year. That may not mean a lot to you. We haven't covered radiation yet. We'll do that a bit later. But to give you a comparison, a full body dose of 5 sieverts is deadly. So if you were to be exposed by 5 sieverts of radiation in one hit, you would die, guaranteed. These satellites with a 3 mil aluminium shield are still receiving 25 sieverts per year. So over 5 times the lethal dose to a human, just by whizzing around in space. The Apollo missions were one of the first where humans actually had to travel through these Van Allen belts. So to leave Earth and get to the moon, we had to pass through these belts. They managed to do it in such a way that they avoided the inner belt. They sort of lined up their trajectory such that they missed the inner belt and only passed through the outer belt. And they did that in a very direct path to reduce the amount of time. And given that the outer belt is a lot thinner and a lot less concentrated, the radiation is significantly less than passing through the inner belt. So their overall exposure was really just dominated by the solar particles once they were actually outside the Earth's magnetic field, rather than the particles and the radiation exposed from hitting that outer Van Allen belt. The radiation that they received from their mission varied a little bit depending on the solar activity at the time, the path they took, the time they were out there, etc., etc. But on average, they measured between 0.001 and 0.01 sieverts. This is much less than the standard of 0.05 sieverts, which is set by the United States Atomic Energy Commission. So that's people that are working with radioactive substances. They can only be exposed to 0.05, which is 50 millisieverts every year. And on average, the astronauts are getting less than that. So we're doing pretty well just in that aspect, but that's not factoring in spending long amounts of time in space. In terms of the effect on the body with radiation, it has 2 main types. You've got somatic and genetic effects. The high energy radiation can destroy and mutate the DNA, which is what we call the genetic effect. And it also can cause things like radiation sickness, radiation burns, and things like that. And that is the somatic effect. So there's a couple of different things here. Some different examples about the inflammation, scarring, seizures, skin burns, the radiation burns, etc. And in case you didn't know, the old school candle wicks that they use for camping, it's kind of like it almost looks like a flimsy miniature like Hessian sack, and you attach that to your gas lamp and you set light to it and it just glows. That is actually a radioactive substance, so it's actually an alpha particle emitter. So those things are quite radioactive. So if you've still got one lying around, don't freak out. You generally don't get close enough to them and handle them, but just be aware that's a commonly used item that is actually quite radioactive. In terms of genetic effects, this is fairly well known in today's technology, and this is from the radiation having such power that it can strip your DNA and it can actually destroy and mutate the cells. Sometimes the issues with this is that it can actually pass down through generations without showing itself, and maybe 2 or 3 generations later suddenly these defects appear or these mutations start to show. So it's not always directly visible on the person that's exposed to it or even their children, for example. So when we look at the somatic effects, these are just the ordinary cells in the body that are being damaged. It's not your DNA as such, and it's not your reproductive cells. So it's just ordinary cells. And I make that sound less serious than it is. It is still very serious, but it's not something that you will pass on. It's something that will just be exposed to you. So you can have things like nausea as sort of the lower level. If you get to 2 sieverts as a whole body dose, death generally is unlikely at this stage. You get radiation sickness, which is generally your nausea, your vomiting, you start to have burns, your hair might fall out, things like that. They're all different sort of stages of radiation sickness. And if we get up to the 4 to 5 sieverts, remember that was the lethal stage. 4 sieverts, we've got a 50% likelihood of death within 2 months. So radiation is not a nice thing in that sense. You will have very severe radiation sickness at this point, and there's a very, very high chance of something like leukemia and tumours developing in future. And if you manage to get up to 8 sieverts, you've got an almost certain death within 1 or 2 weeks. Acute radiation sickness, you have convulsions, lethargy, stuff like that. If anyone's seen the HBO miniseries about Chernobyl, the documentary sections that they showed about the firefighters and what happened to them, that's an example of sort of 8 sieverts and more. They were exposed to significantly more, but that unfortunately paints a very accurate picture of the kind of things that radiation can do to people. So to give you some perspective here, this is a table of different sort of radiation exposures. So you can see that the banana is actually a radioactive substance. Believe it or not, bananas are radioactive. But we're talking 98 nanosieverts. It is very, very small. So don't freak out. If you eat a banana, you're not going to die or you're not going to get radiation sickness. It is completely fine. You would have to need to eat a ton of bananas before you would have any issues. Annual dose of flight attendants is 1.5 to 1.7 millisieverts. A full body CT scan, which is quite significant, is only 10 to 30 millisieverts still. The Fukushima nuclear accident, they reckon 68 millisieverts. That's getting up there. That's quite a bit. If you spend 6 months on the International Space Station, you're clocking 80 millisieverts just by being in space for 6 months. Ironically, chronic dose for the lungs for someone who is a smoker of about 1.5 packs per day, you're looking at 160 millisieverts. So there's actually radioactive polonium in cigarettes, and apart from all the other things that make cigarettes bad for you, the chemicals involved in them are actually radioactive, and the radiation exposure that your lungs are getting is extreme. And this also contributes to the high risk and high chance of things like lung cancers and stuff because of the radiation exposure directly to your lungs. If we had a 6-month trip to Mars, we're talking about 250 millisieverts. So 6 months trip is worse than smoking 1.5 packs of cigarettes a day for a year. And then we keep going. If we get up to the whole sievert, 1 sievert, maximum amount for the NASA astronauts over their entire career. So if you become an astronaut for NASA, 1 sievert is the highest amount that they'll ever let you before you'll have to retire. And they keep track of that pretty accurately. And we keep going. So these you'll hear about a little bit later on when we cover the radiation topic. I'll give you a lot more information about these guys like Harry Dagley and Lewis Slotin and what happened to them. So let's have a look at Mars. This is a diagram of the radiation exposure in Mars based on elevation. So there's 2 main things here. Obviously, the lower we get, the better it is for us in terms of radiation exposure. The higher we are, the higher the radiation. So we don't want to be colonizing mountains. Even just flat plains close to ground level is not good. The radiation exposure is still far too high. This is sieverts per year. So this is 0.2 sieverts. That's like 260 millisieverts a year, which is extreme. Even if we go to 8 kilometers below sea level, so that's like finding an 8-kilometer crater and living in it, we're still getting 200 millisieverts a year in radiation, which is still far more than the average human can endure. So let's go beyond radiation. The next one is microgravity. So microgravity is this fact that once we leave space, we know that we just kind of float around and there's no gravity left behind. But this has apart from the obvious issues with doing things, drinking, sleeping, all that kind of stuff, it actually has a really negative effect on the body and it causes the bones to deteriorate. So astronauts lose on average 1 to 2% of their bone mineral density every month. On a long duration space flight, such as those planned to Mars, which we're talking 6 to 7 months, bone loss can be extremely serious. Once you're out in space and while you're in space, it's not really an issue in the sense of you don't really notice, and it's fine as long as you don't come back. Once you come back, your bones are suddenly extremely weak and porous, and then doing something like an extreme case, you might get off the space shuttle and jump and you shatter your legs because they're now extremely brittle. They're not designed or they're not adjusted to the gravity of Earth. So we try and override this by a whole range of things. They've figured out that exercise definitely helps. Getting astronauts to exercise a couple of hours every day to simulate that load of Earth definitely helps. But the main thing is that the bone is like the muscles in our body. If you don't use it, you don't put it under load, then it atrophies or wastes away. So we need ways that we can stress the bones, we can put load on them, so that they then compensate for this and adjust by strengthening themselves, which is what they do for us on Earth all the time.
And changing all the time. Our bones are composed of different layers. The outer surface of bone is called cortical bone. This is the smooth, hard part of the bone that we can see when we look at a skeleton. Inside the cortical bone is the trabecular bone. This type of bone looks like a sponge and helps to protect the bone marrow. The constant process of bones growing and changing is known as bone remodeling. This process is carried out by specific cells in our bones. Cells called osteoclasts have the role of breaking down our bone and removing any parts that need replacing. At the same time, cells called osteoblasts have the job of making new bone and helping to repair any parts of the bone that have been damaged. On Earth, in healthy individuals, this process is normally balanced so that the same amount of bone is made and broken down. In space, astronauts are exposed to lower levels of gravity than on Earth. This means that they have less mechanical stress put on their bones as they move around. Scientists believe that the bones naturally try to adapt to this new environment by increasing the rate that the bone is broken down by the osteoclasts. Meanwhile, bone formation continues to occur at the same rate as it does on Earth. The result is an imbalance in bone remodeling, which leads to an overall decrease in bone mineral density. While in space, astronauts can manage with lower bone density, but when they return, their bones are less able to cope with Earth's gravity. This increases the risk of fracture and injury. Scientists use many different tests to measure the density of the astronauts' bones. Results show that the astronauts, while in space, lose bone in a similar pattern to people on Earth who suffer from osteoporosis, but the astronauts lose it at a much faster rate. Scientists have found that exercise, when combined with good nutrition and increased vitamin D intake, is able to preserve some of the bone that was previously being lost. Since 2008, astronauts have been able to use a new exercise machine called the Advanced Resistive Exercise Device, or ARED. It is thought that this increase in force triggers the formation of new bone, bringing more balance to the bone remodeling process and allowing the bone density to stay at roughly the same level as it was before the spaceflight. It is a significant achievement to be able to maintain bone density in space, but more experiments need to be carried out to see whether the new bone which is formed in space has the same structure and strength as new bone which is formed on Earth. Understanding bone loss associated with microgravity may lead to better preventive care or therapeutic treatments for people on Earth suffering bone loss as a result of bone diseases like osteopenia and osteoporosis, or for patients on prolonged bed rest.
I'm going to finish up with a little video. This is a film clip, and this was actually real. So all of the stunts they did in microgravity simulation, using a plane that flies up quite high, and then it basically drops to simulate a free fall situation. And so you inside the cabin, you can't necessarily tell that you're free falling, but the result by everything around you, everything floats. So it simulates this microgravity effect.
Looks like it's time to decide. Are you here? Are you now? Is this it? All of those selves that you tried, wasn't one of them good enough? 'Cause you're upside down and inside out, and you can feel it. Inside down and upside out, and you can feel it, feel it.